We are Team 7 from Engineering Challenge 1. I'm Dylan.
I'm Huiyu, and
And
this is our video for the Engineering Challenge 1 project. First, video of FPGA running the two programs will be displayed.
Select the program counter after the particular instruction when fetching 1, so fetching 1 and after the instruction, it's then brought in the rest of the part here. So we want two different registers. So first the address is going in here. So
now, we will begin explaining different parts of our processor. We first start from the program counter. The program counter is a 32-bit resettable enable register made from our resettable enable D flip-flops. When the register is reset, the program counter sends an output to the ROM, also known as the read-only memory. The program counter will only deliver bits on the rising clock edge. Moving on, we talk about the ROM. It is where all the instructions of a program are stored. It is an instruction memory. Here, we use assembly language to write our squares program that will be shown and explained later in this video. We use three different types of instructions in our ROM, namely R-type, I-type, and J-type. All of these different types of instructions have different bits assigned to them. The ROM then transfers the instructions to the control unit, the reg file, and the sign extent.
Here we have the reg file. It is a series of registers. A register is a fast memory storage constructed from our D flip-flops. The ROM passes data to the register file, which then passes data to the data memory through the ALU. Control unit is the part that we are most proud of. It is made from two parts, the main decoder and the ALU decoder. The main decoder directs the operation of the other units. It takes in and deals with the 6-bit opcode from the most significant instruction bits. Then it gives out a number of outputs which can be either 1 or 0. These outputs tells the processor how to respond to the instructions that have been sent in. If we take a look at the inside of the main decoder, it actually consists of the combinational logic gates we get from the K-maps of the main decoder. Now we move on to the ALU decoder. The 2-bit ALU OP inputs here and the 6-bit function input here feed the ALU decoder. In the ALU decoder, by checking the K-maps, we can see that when this input ALU OP1 equals 0, we don't care about the function input anymore, which refers to the bottom part of the ALU decoder, where we directly set subtraction and addition, which are 110 and 010. While in the other case, we just use another block consist of combinational logic gates and the 6-bit function input. And both two cases lead to the final output of the ALU control, which is a 3-bit bus line output to the ALU. Now we take a general view of the control unit. The red DST feeds to the 5-bit multiplexer and then outputs to the write address 3 in the register file, while the reg write feeds to the write enable 3 in the reg file, and it determines whether the address we get from the 5-bit multiplexer will be passed into the reg file or not. The ALU source outputs to the 32 bits multiplexer here, and then pass on to the ALU. The branch will firstly connect with the 0 output of the ALU using an AND gate, and then feeds back to the multiplexer at the very left. Memwrite causes the SW instructions to write to data memory with the data it gets from the register. Memotorec determines how the ALU will work and whether the ALU will pass the address to the data memory or not. And then jump feeds back to the multiplexer here, and it determines whether we will go in the jump loop or not. Finally, the ALU control tells the ALU which operation it will conduct, including addition, subtraction, and or an SLT. Now we move on to the ALU, also known as the arithmetic logic unit, performs arithmetic and logic operations. It receives the 3 bits input ALU control and 2 32 inputs from reg file. The output is also a 32-bit bus line, which will then feed into the data memory, the 32-bit multiplexer, and the display driver.
Next, we will talk about the display driver. The display driver is made up of 2 32-bit inputs, a 32-bit address bus and a 32-bit data. Values are displayed using a 7-segment display. For example, when the address is FFF0 and there is a rising edge on the clock, our FPGA shows the value stored in the register. When the address is FFF1 and there is a rising edge on the clock, 0 is stored and the display is switched off. Also, we turned off the decimal points by using 8 bits instead of 7 bits as done in Lab 4 earlier. Moving back to the sign extend. The sign extend extends the number to more bit. The inputs are 16-bit. However, the IMs are used in the 32-bit register. Sign extend is used to convert the 16-bit value to a 32-bit value by filling the first half. For positive IMs, the first half is zeros, while for negative IMs, the first half is ones. Then, the output is delivered to the left shift and the 32-bit multiplexer. From the left shift, the instruction memory is multiplied by 4 and it feeds into the 32-bit adder, which then outputs to the 32-bit multiplexer here.
This is one loop of a processor, and the program counter will now be reset, and new instructions will be given out from the ROM. And then a new cycle will start. Now, we will show the simulation of the ALU. First, we will try subtraction. It works pretty well, and then we will try AND.
I'm not going to break that.
It also works good. Finally, we will try OR.
You want this before the ALU or after?
So this is all of our simulation part.
Finally, we start to explain our square numbers program. This is our square numbers program that we wrote. In the first line here, we add 0 to 0 and store it as st1. In the second line, we have st2 where we used add-I to add 1 to 0 and store it as st2. Now, we go into our loop. In this line, we send the value of st1 to be displayed to the FPGA, which is 0, our first value. Next, we add st2 to st1 and store it as the new value for st1. Then we use add-I to add 2 to st2, which gives 3 for st2, and we have a j loop which loops back and displays 4 on the FPGA. This keeps looping to display further values such as 9, 10 which is 16 in hex, and 19 which is 25 in hex, etc.